Okay. So, like Soichiro said, this is joint work with Nicole, who's here on the call, but physically has moved away from Harvard to New Jersey. And so what we kind of did in this paper is we took a look at noncompliance in kind of a general class of factorial experiments, 2 to the k. And so I'll try to kind of give some motivation for what we're trying to do here. Basically what we're trying to do is to randomly assign, factorial designs are basically, are designed to randomly assign multiple factors at the same time. And these are extremely common in the social sciences and beyond because they allow us to answer a number of different causal questions in the same experimental design. So we can do things like estimate marginal effects of one of the factors, joint effects of 2 of the factors, or interactive effects between different factors. But almost all of the analyses and methods designed to handle or to analyze factorial designs basically assume perfect compliance with the treatment assignment. And in the social sciences in particular, but beyond that, this isn't a particularly good assumption. Just to give you a sense, in kind of a canonical case in political science where we have non-compliance, get out the vote phone call experiments where you're randomly assigned to receive one phone call or another, or phone call or not. There we have compliance rates of at most maybe 20%, and that's been going down over the years. So it might be down as low as under 10%. So that compliance here means actually picking up your phone. So this paper in particular is going to basically present a framework for 2 to the k factorial experiments with non-compliance. And so the kind of the concrete things that we're going to do is when we're going to generalize the kind of standard instrumental variable assumptions you see in a binary context, a single factor experiment. And we're going to generalize the estimands that you have, the kind of quantities of interest, to the factorial setting. So we're going to merge those two kind of literatures. We're going to define what it means to be a complier in this scenario, which is slightly different than what you have in a normal instrumental variable setting. And then we're going to show how to conduct both finite sample, and then in the paper, at least in the appendix, we do a little bit of Bayesian inference for these experiments. And this is all going to generalize some previous work that I had done on the 2x2 case for get out the vote studies. And we're going to apply this, at least I'll talk later on about a particular application, which is a field experiment by Chris Blattman and co-authors, where they were really interested in could we kind of prime or change non-cognitive skills to reduce what they called antisocial behavior, which are basically violent crimes and criminal behavior. And so the way they went about this was they had a factorial design with 2 factors. One was just a straight cash transfer. And the second factor was an 8-week group cognitive behavioral therapy. And this was the factor that was supposed to lead to a decrease or a kind of a improvement of non-cognitive skills, so to speak. So this was in Liberia with about 1,000 young men that had been previously either violent or had engaged in criminal activity.
Sorry,
and they looked
Matt,
it up.
to interrupt.
Yeah.
The slides are not moving. Is that?
Oh, yeah. No, that's bad. Okay.
Okay. Yeah.
Yeah. Let me. All right. Okay. This is fun. Okay. Can you see that? Okay. Well, we may have to deal with the kind of like Chrome of this. Okay. All right. So just to kind of pick up where I was saying, we have the outcomes here at the short term, at the 2 to 5 week stage, and then also at the long term, the 12 to 15 month stage. And they looked at economic outcomes, the antisocial behaviors that I talked about before, and then also one thing that I'll kind of go over today, which is a kind of a mediator that they looked at, which was quality of social networks. These are things like how supported you feel by your family, antisocial behavior in your networks. And so there was kind of varying rates of non-compliance across the these two different factors. So as you might imagine, compliance is very good with the cash treatment. About 98% of people actually took the cash if they were assigned to it. But there was more non-compliance in this cognitive behavioral therapy arm, depending on how you measure compliance in that setting. In the paper, we'd look at another application, which is a 2 by 2 by 2, so a 2 to the 3 field experiment, get out the vote with 3 different modes of mailers, phone calls, and and door-to-door canvassing to look at kind of a higher order setting. So let me just kind of quickly go over the framework that we're in here and how we're going to generalize things from the case of the single treatment framework. So just to give you a review, if you guys are not familiar, a lot of you are, but the kind of basic IV setup is that we have some randomized treatment assignment Z that affects, is affects but is not deterministic equal to treatment uptake D, and in particular because it's the case that that there's D is self-selected usually. Uptake, you get to decide whether or not you take it up. We usually think that there's unmeasured confounding between that uptake and the outcome. So because of that confounding, the average treatment effect of treatment uptake on the outcome is identified. So the kind of usual game that people play in this setting is to just change the estimand to something that is identified. And the way that this ends up looking is that we're going to define some potential outcomes. So di of Z is going to be what unit I's uptake for assignment Z would have been. So do I take the cache if I'm assigned to cache? Do I take no cache if I'm assigned to no cache, and things like that. And then we'll also have potential outcomes for the outcome as well. So this could be the unit I's outcome under assignment Z and uptake Z. Okay, so you might respond differently to treatment uptake if you're assigned to different assignments. And the basic approach here that people have taken in the past, or at least one way to approach this problem, is to do principal stratification, which basically is going to take units and stratify them based on their uptake profiles. So usually these are given kind of nice names in this setting, and there are people that are compliers. Those are people that whose treatment uptake is always equal to their treatment assignment. And then we have other people that are different kinds of non-compliers. So you have people that are always takers, people that always take treatment, no matter their assignment, never takers, people that never take treatment, even if no matter their assignment, and then defiers, people that take the opposite of whatever they were assigned to. Right, and so once principal stratification works by taking these and then kind of again, the principal strata, and then working with that in order to change the quantity of interest. And in particular, what the single factor IV does is it looks at usually a ratio of intent to treat effects. And they just look at, say, the ratio of the intent to treat, just the average treatment effect of the treatment assignment on Y, the outcome, divided by the intent to treat effect of assignment on the uptake. And under this kind of principal stratification approach and a couple of key instrumental variables assumptions defined by Angrist, Estimands, and Rubin, this is going to have a special interpretation. And these two assumptions are the exclusion restriction, which just says that once you fix the treatment uptake, the treatment assignment no longer has a direct effect on the outcome. And monotonicity, which here in math, but basically means that it rules out the possibility of those defiers that I talked about a second ago. There's no one that has this pathological behavior doing the opposite that they're assigned to. And under these two assumptions, this tau, this ratio of intent to treat effects, is equal to the local average treatment effect, or the treatment effect among compliers. And so this is a pretty cool thing, right? Even though there's unmeasured confounding between the treatment uptake and the outcome, we still are able to recover at least the treatment effect for some group that's maybe a scientifically interesting group, the people that actually comply with the treatment. Okay, so in order to move to the factorial setting with arbitrary factors, things start to get kind of messy notationally. I'll try to keep it as much track, as easy as possible today. But what we're going to work with is we're going to have, instead of 0, 1 factors, we're going to end up with k binary factors with levels -1 and +1. This is a little bit different than political, we're used to in political science, but this is the kind of standard way that people in the factorial design literature write their factors. And then we're going to have treatment assignments that are going to be a vector, a k-length vector of how you're assigned to each one of those factors. And then we're going to have, again, a treatment uptake vector, which is, again, how you actually, whether or not you actually took your each one of those factors. And both of these are going to have 2 to the k possible values. But there's 2 to the k possible ways that you could be assigned to treatment, and there's 2 to the k possible ways you could actually take up treatment. And we're going to define now everything just goes from being kind of regular font to boldface font, just to indicate that everything's a vector now. So now that we have this di of z, this is just how people, how my treatment uptake vector would look if I was assigned to the treatment assignment little z. Okay, and so non-compliance again just means that if it's the case that, it's not the case that everyone has di of little z equals little z. So some people deviate from at least one of the factors. And then again, we're going to just define the potential outcomes here as a function of treatment assignment and treatment uptake, z and d. And today I'm mostly going to be working with just kind of redefining those in terms of this kind of composite potential outcome, which is just the potential outcome just as a function of assignment, letting d take whatever value it would take for its potential values that it would take. Okay. Any questions so far?
So just a quick question. So D is also coded as -1 and 1. Is that right?
Yeah. So they're coded exactly the same.
And when you say non-compliance, I guess you could also define non-compliance with respect to each factor, but
yeah.
Okay.
So I'll get to that a little bit later in terms of defining what a complier means and different types of compliers.
Right.
Okay, so now the thing to do is to kind of generalize. I talked about some of those IV assumptions before, and so now I'm just going to generalize those instrument of variables assumptions to the factorial setting. And some of these, a lot of this is somewhat straightforward. Some of them are more tricky, and there's a new assumption that we need here. The first is that we're just going to assume a particular experimental design in this paper, and that's that the treatment assignment is completely randomized. Although what we end up doing in the paper is that we just kind of, if you have something where it's kind of a Bernoulli design on each one, you can also independently randomized. You can also just kind of condition on the number of treated in each assignment level, and proceed as if it was a completely randomized design. We're going to assume monotonicity for each one of the factors. So all this is just saying is that there are no defiers on any factor, regardless of what the other assignments are. So no one's induced to be a defier by some other treatment assignment. We're going to make the outcome exclusion restriction, which is just the fact that, again, the same thing here, just in vector form. And then finally, we're going to make this treatment exclusion restriction. And this is going to be the big one for our approach, and one that we weakened to some extent in the paper, but is kind of a big part of what we do, which is just saying that basically the treatment uptake on factor K is only a function of treatment assignment on that factor. So it's not the case that the random assignment to cache doesn't have any effect on whether or not you take treatment, whether or not you actually comply with the cognitive behavioral therapy treatment assignment. Okay, and so this implies no.
Clarify a question.
Yeah.
So does that mean that you kind of assume away the interaction in terms of encouragement, but you still have interaction in terms of take-up?
Yeah.
Among factors.
Yeah. So that's there's the next line here is that, so basically what this implies is that there are no interactions in the effect of assignment on the DI, the uptake. So this might be really implausible, and I can give you a DAG here that kind of shows you how this looks, where basically what we're ruling out are these cross arrows, the idea that the ZI of the assignment on factor 1 affects the assignment on factor 2. No, sorry, the uptake on factor 2. And so, and this is a very strong assumption that it might be implausible. There are a couple of things that are not necessarily in its favor, but are useful about it, is that this is actually a testable assumption. So you can actually you can evaluate whether or not you see interactions of Z on the different D values. And so that's one way you can, it has testable implications that you can look at. And we looked at that in the applications, and we don't see any evidence of those things. But also we've done a little bit of work to weaken this assumption and try to still maintain some of the interpretation of the quantities of interest that I'm going to show you. But in order to get the kind of cleanest possible interpretation of the quantities of interest, this is the kind of assumption that you need to end up making. And especially it's the case that if you want to investigate interactions in a serious way, between of D on the outcome, then you do need to make some restrictions on the kinds of interactions that you have in the first stage. So that's like a trade-off here that ends up that we find in this paper. Okay.
So are you saying it's possible to say flip the restriction where you have no interaction on like outcome, but then allow interaction on the
we actually haven't done that part of it. We haven't actually restricted it in that way, but I think you could. I mean, you may have to. It may be the case that would work. I think you would have to. I think the way you would show that is with a binary. Easiest way to show that is with a binary outcome, and then and then you can just work with all of the huge number of strata. And then as they collapse on each other because of that assumption, I think you would end up with something that you could identify. And just to be clear, that this assumption is not necessary for estimating the marginal effect of one of these factors on the outcome. It's just going to be the kind of joint effects or interaction effects that are going to be more problematic. So yeah, you still get like say the marginal late, or in this case, if you weaken this assumption to some extent. Okay. And so when you make these assumptions, you can basically under all of these assumptions together, what you end up with is every unit can be categorized into a bunch of different compliance types or principal strata. And in this case, no, they're not just 3; there are 3 to the k. And so we'll have this TI vector, which will be someone's compliance type. And so it'll just basically be each element of this vector is going to be either a C or an A or an N, indicating whether that person is a complier, an always taker, or a never taker on that particular factor. And again, to get to this definition or this characterization of the compliance type, you need this treatment exclusion, because that is what ensures that the compliance on one factor is orthogonal to compliance on another factor. Again, you can weaken this and make them functions of the others, but it's in the paper, but I'm not going to present it today. Okay, so what are the actual estimands that we may want to deal with in this particular setting? So if just to remind you, again, in a single binary treatment, we look at the ratio of intent to treat effects, right? We look at the ratio of the intent to treat of assignment on the outcome divided by assignment on the uptake. So how do we generalize that to the factorial setting? And in particular, this is difficult because there are just, as you might imagine, there are just lots and lots and lots of different effects that you can estimate in a factorial setting. And so we need some way of organizing all of these things together. And so the way we're going to do this is use this framework, this factorial effects framework by Dasgupta et al., which was the kind of one of the first ways of papers that dealt with defining treatment effects in the factorial setting in terms of potential outcomes and kind of and so what they did, and so what we're going to use from them is that we're going to collect all of the potential outcomes for a particular person in this kind of YI bullet. And that's going to be, for instance, imagine for the 2x2 case, that's going to be, YI of treated, control, treated, control, and control, control. So it's just a vector of all the possible potential outcomes. Again, just for treatment assignment. And then what we can do is we can define all kinds of intent to treat effects through these, what are called these contrast vectors, which are just, they're L dimensionals. So they're 2 to the k dimensional vectors with 1/2 being +1 and 1/2 being -1. We are going to organize them by the little subset J is going to be organized by the level of interaction. And what they do is they basically are going to kind of allow us to compactly write down treatment effects. And so the first k of these vectors correspond to main or marginal effects of factor J. And then the next k choose 2 are going to be the 2A interactions, and then the 3A interactions, all the way up to the k-way interactions. And so this is just a way of kind of organizing all of the effects. And then we can actually define individual level causal effects fairly compactly as this. So 2 to the negative k minus 1, and then the product of G sub J times this vector YI. Right? And what this is doing is this is just kind of selecting out the right contrasts, and then taking the average of them, marginalizing over the other vector. And I'm gonna just I can do a quick example of this just to kind of give you a sense of the way this works. So here's in a 2x2 case, right? You have, these are just the 4 different, here are the 4 different potential outcomes, and here are the 3 possible these G vectors that you could have. And so the first one is just +1, -1, +1, -1, again, 1/2 plus, 1/2 minus. And so when we do this calculation that I just showed you, what we end up with is taking the difference between, you know, the effect, basically what this looks like is the effect of factor 1 when factor 2 is positive, plus 1/2 the effect of factor 1 when factor 2 is -1. And so this generalizes that the G2 is going to be the same thing, but flipping the order of them. So those are going to give us the 2 main effects, marginalizing over the distribution, marginalizing over the other factor. And then the third of these is going to give us the interaction, which is going to be just kind of selecting these out in the right way to get the interaction. And we've gone with the kind of traditional 1/2 kind of equal weighting for each one of the different profiles, but you could also use your own distribution over the different profiles if you thought that was useful in a particular context. Okay, so once we have these, we can define the kind of quantities of interest, at least the intent to treat. We'll go ahead and get the population average potential outcome. So this is just, or the sample average in our, you know, population in the sense of like the population of our study, so all the people in our study. And then we're going to define the finite sample average intent to treat factorial effects. It's a bit of a mouthful. And then these are just the tau sub j. So this is basically taking that and taking the average of those individual level causal effects. What we're going to have is these different ITT effects are going to correspond to different main or interactions. And the interpretations are, for the first k of these are just the main average effect of factor j, marginalizing over the other factors. And then for any j greater than k, the number of factors, these are just interactions. And it's interaction among some of the factors marginalizing over the rest. And so these are similar in some sense to the average marginal component effects that you see in conjoint designs, although again, we're assuming a particular marginalization distribution. And just to emphasize that these are effects in the sample. These are not kind of hypothetical populations. So these are finite sample quantities of interest that we may want to estimate. And again, this is just the main effect of factor 1 is just this average. So it's the average effect of factor 1 when factor 2 is +1, and the average effect of factor 1 when factor 2 is -1. And then we have the interaction as well, the difference between those two effects. So that's what these things have. So the actual, once you get down to it, these are very intuitive effects, but it's just kind of organizing them in a way that's easy to scale up to arbitrary k is a little bit tricky. And so an even trickier thing for us is how do you define intent to treat for treatment uptake as opposed to treatment instead of on the outcome. And so we're going to do this in a particular way, but to do that, we need to define what we call the active factors. So for any particular factorial effect, right, it's either a main effect of some variable or it's an interaction between multiple factors. And so what we're going to say is for any effect j, we're going to take all of the ones that are either being interacted or it's the main effect, and we're going to call those the active factors for that particular effect. And for a 2x2, for instance, the j equals 1, that's the main effect of factor 1, so the active factors there is just the first factor. But for the third, the third effect is the interaction between these two, and so the active factors there are 1 and 2 together. And the way we're going to end up defining effects on treatment uptake is to actually just create a new variable, which is the product or interaction between these active factors. So literally take the two variables, the two d variables, and multiply them together. And what we'll do is we'll just take the average of those effects, of the effect of z on those interactions. And so what this ends up looking like is that, you know, the treatment uptake intent to treat effect is going to be the delta 1. The first one is going to be the main effect of z1 of factor 1 on treatment assignment, on treatment uptake for factor 1. Same for effect 2. And then effect 3, this is where things get different, is that it's the interaction effect of Z1 and Z2 on the product of D1 and D2. Right, so this is a little bit complicated, and it may not seem obvious why we might want to do it in this way, but these are going to be also finite sample quantities of interest. And the reason why we end up doing it this way is that under the IV assumptions, these things end up identifying a particular kind of complier, similar to the way that the ITT of Z on D in the bivariate or the single factor case identifies the complier. Any questions about this? I know this is like a little weird.
I have a quick question. Sorry,
yeah.
Going back to the same point.
Yeah.
So how does this delta 3 is different from assuming away the interaction between Z's on D?
Is it, wait.
There was assumption that there's no interaction between the achievement, like encouragement on the takeoff. Yeah,
so there's no interaction between on the effect on D1 or D2, but there may be an interaction on the multiplying those two things together.
I see.
Right. So it's not. So it would rule out, let's say, if we replace this D1 times D2 with either one of those component effects, yes, that effect should be 0, but the product of them doesn't necessarily need to be 0.
I see.
But this is like a real product. Like it's
yeah, just like multiply these two together.
Right. So it's basically whether you're taking up both treatments or not taking up either.
Yeah, exactly. Yeah.
So a quick question. So DI1 and DI2 here are coded as 0, 1 or negative 1, 1?
A negative 1 plus 1, yeah.
So if both are negative 1, their product would be 1?
Yeah, that's right.
Okay. I see.
Yeah, it's not like, again, coming at least from my perspective, when I first came to this, it's not intuitive, and I have to keep reminding myself about these things, but that's how these things that's how they're defined.
Yeah, so it's a bit counterintuitive to me, like the social said, it's there's no interaction on D1 and D2, but there is an interaction on their products.
Yeah. Right. In particular, it's going to be, again, what this is going to do is this is going to find people that are compliers on both of these treatments. That's like that's what delta 3 ends up being in this case. And again, without that, and that relies on the treatment exclusion assumption, because again, if you allow for those interactions, this could be picking up both the interactions for D1 and D2 separately, but also these joint people that comply on all of the treatments together, and you can't differentiate between those things. But once you get rid of those other interactions, all you're left with are the people that comply with both. So yeah, it's not particularly, it's other than it kind of having this vague kind of similar form to the binary case, it's not, I wouldn't say it's super intuitive.
So one thing that might be helpful, if you don't mind,
yeah.
Under our assumptions, basically, you can also think of this as just doing the product of ZI1 with DI1, and then the product of ZI2 with DI2 and multiplying those, you'd get the same final number under our assumptions. So this is just a more convenient way to write it in kind of this nice vector formation where we have our Z's on one side and our D's on another.
Yeah. Okay. So then what we can do with these things is take all of these factorial effects of assignment on the outcome and all of these factorial effects that we have on this, sorry, this D star should be D tilde, on all of these kind of interactions that we talked about. We're just going to take the ratio of them, just like you would do in a univariate case. And without any the IV assumptions that we talked about, this just has the interpretation of a ratio of effects that, whether or not you think that's an interesting quantity. And then, but with the factorial IV assumptions that I brought up earlier, like I was saying, this delta sub j is going to be equal to the proportion of compliers with the active factors for effect j. Right. again, marginalizing over the inactive factors, kind of regardless of their compliance status on the other things. And the phi sub j is going to this ratio of these two is going to be what we call the marginalized complier average factorial, or MCAFE. And this is going to be the average factorial effect among people that comply with both of the with all of the active factors. Again, marginalizing over their compliance status on other factors. So it's so in the case of like so if you just look at the main effects, so this is recovering something like the late for them. It's the people that would comply with one factor marginalizing over their compliance with all of the other factors. And that's one situation where you're less reliant actually on the treatment exclusion restriction. You can actually weaken that and you still get something that looks like a late in that context. But this has this nice interpretation. Again, you do these ratio of estimated effects and we get this nice interpretation, kind of very similar to what we had in the case of the binary or the univariate case. So one more quantity of interest that we need to talk about, one problem with this MCAFE, or the marginalized complier effect, is that as you're changing the effects, you're going from, so effect one, main effect one, main effect two, the interactions, and so on and so forth. The conditioning set, the compliance group, is changing across those factorial effects because the active factor group is changing, right? So that's going to be it could make it difficult to compare things like main effects to interactions, or even compare. If you're comparing two main effects of two different factors, right, you're talking about effects on two different subgroups of the two different strata. So if you think about the example in a 2 to the 3 design, and you have if you're looking at the interaction between factors 1 and 2, right, a marginalized complier is going to be someone that either is complier always taker, complier never taker, or complier. It's a complier on everything, right? So but if you would move up to the interaction between all three, obviously the only thing that would be left would be the compliers, all of the compliers. So one alternative that you can do is to try and estimate or redefine effects among people that comply with all factors. And we call these perfect compliers. Thanks to Kosuke had that idea for a name. And these perfect compliers are people that all the people that have the TI equals comply on all the different factors. And we have this gamma sub j, as we call the perfect complier average factorial effects, the PCAFE. And you can also write these as a ratio of two different intent to treat effects, but it's just a lot more complicated because you need to kind of deal with some kind of doing some somewhat complicated algebra to kind of difference out the different groups that you want to get rid of. So these other groups need to be kind of dealt with in some way. And so it's just a slightly more complicated expression, as if the last one wasn't complicated enough. So I won't kind of hit you with that. Any questions? Okay, well, I'll keep going, and if folks have questions, obviously just feel free to interrupt. So we've defined these two, at least these.
Sorry,
yeah.
Quick sort of question. So for the perfect compliers, you could estimate, I guess, bias effects. You don't have it doesn't have to be a joint treatment effect. It could be marginal effect for each factor.
Yeah. Yeah, all the different J's are different.
Right. That's the only group that you could possibly identify the joint effects. Is that right? Yeah.
So the last
all effects, I guess you could identify all effects and then compare.
Yeah, if you wanted to compare all the effects, you'd have to do it among those, without making strong assumptions about the different compliance groups or something like that. And just one more point that is maybe clear but maybe not is that this perfect complier effect is equal to the marginal complier effect for the k-way interaction. So for the highest order interaction, those two things are equivalent to each other, right? Because
but those effects are useful because you can basically compare, right? Because it's the same group of people, so you can. Yeah,
the trade-off, obviously, and you'll see this when I show some results, is that there's a much smaller group typically,
right.
And so the power issues are really bad, and so it's a little bit, it's actually a very strong trade-off in some cases, and so I don't, other than or I'm not saying which is better, but it is like you do have a trade-off there in terms of these things. So those are the different, at least the ones that kind of quantities of interest that we discussed in the paper, there you could come up with more, but those are the kind of organizational principle that we were able to come up with for dealing with, 2 to the k minus 1 of these different effects. And now let's talk a little bit about inference for these quantities of interest. And so, so we have observed data where, the actual, once we run the randomization, we have a set of treatment indicators, WI sub L, and that just says if that's equal to 1, if you are assigned to the level Z sub L. We'll have the number of different units that are in each one of these levels. And then what we can do is we can just get the average observed potential outcomes for each one of those levels. So this is basically just saying, this is a fancy way of writing, just take the averages within each one of the treatment levels, observed treatment levels in the data, and just take those as your estimator. And then so basically what we can do, this is not so that surprising, what we're going to do is we're going to estimate, say, the intent to treats for the outcome by replacing all of those sample level or population level averages with our the ones in the actual groups that were assigned to treatment. And so that just, again, looks like replacing all of those things in the way you would expect. And so this is not these aren't particularly interesting estimators once you've defined the quantities of interest. And so you have a similar set of estimators for the uptake on for the ITT effects on treatment uptake. And so because these are randomized, we have that both the ITTs are unbiased for their effects separately, but not necessarily for the ratio. The ratio is not necessarily unbiased, but we're going to come up with a way to do some inference on the kind of standard or the kind of straightforward ratio estimator, which just takes those two ITT estimators and divides them. And you have a similar setup for the perfect complier. So we're going to focus in this paper, at least the main part of the paper. In the appendix, we have some Bayesian stuff, but we're going to focus on finite sample inference or finite population inference, depending on how you say these things. And the basic idea here is that we're going to view, and most of you are going to be familiar with this, but maybe some folks aren't. But in this setup, we're not going to think too much about the data generating process that led to the outcomes. We're mostly going to view the potential outcomes as fixed features of the sample that we have. And we're going to view randomization of the treatment as the only source of variation that's kind of coming in. So that's going to be the only source of kind of variation across repeated randomizations. And again, we're not going to make any assumptions necessarily about the data generating process of the outcome. So it's one nice thing about this is that we don't have to worry about those assumptions about that at all. Now, finite sample inference usually proceeds by testing what's called the sharp null hypothesis of no effect. Right, and that sharp null is pretty strong. It says that for any unit and for any two levels, that their potential outcomes are exactly the same. So this just says that there are no effects of any of these treatments, any of these factors on the outcome. And so there's upsides and downsides to the sharp null approach. One upside is that once you make this assumption, all of the potential outcomes are known under the null hypothesis. So you can fill in the quote unquote science table. So you can fill in what would have happened to every unit under that null hypothesis in all of the different treatment conditions. And so then hypothesis tests just become a computational problem. All I have to do is figure out, well, if I were to re-randomize, what kinds of different effects would I get? The downside is that this is a very strong, often fairly implausible null. I think especially in these factorial settings where you have lots of different factors, and you're going to assume that all of them are exactly equal to 0. So the alternative that we're going to follow here, and this builds off some work that Nicole has done and other folks have done on what are called finite population central limit theorems. So I guess it's not surprising, there's a central limit theorem everywhere. And so there are ones for finite population settings as well. And what these are basically, it's a slightly different mindset, but basically what we're looking at is that we're getting normal approximations for estimators as the finite population sample sizes grow. So we're going to think of a sequence of populations that are growing in size, and we're going to think about what are the properties of our estimators as the size of those populations gets bigger. And when you do that, a recent paper by Li and Ding showed that the joint distribution of these ITT estimators are going to be approximately normal in large finite samples. And that's going to allow us to do things like construct confidence intervals for these quantities without necessarily making, again, any assumptions about the large sample or the data generating process of the data. We're just relying on asymptotics, which fine, and then also the randomization. And so once we have this distribution, there are two broad ways that we could construct confidence intervals for the ratio estimator. Right, obviously for these ITTs, there's very straightforward ways of constructing things. One would be just to use the delta method, right? We have these two ITTs are, once normalized, they're going to have large sample approximations that are normal, and we could use their joint distribution in the large samples in order to get an estimate of the variance of the ratio. Right? This is a very standard thing to do in IV settings, and you can construct 95% confidence intervals by doing plus minus 1.96 times the square root. The problem with this is in these situations in IV, this actually is when there are very few compliers and the denominator is very close to 0, you can actually end up with very bad performance of these and kind of wild estimates, and then also lots of undercoverage. So the approach that we kind of highlight in this paper is got a bunch of different names, but the one that we settled on is Fieller's method, because Fieller was one of the ones who first went with it. And the idea here is, and I'll talk about it more in a second, is to analytically invert a test statistic, a hypothesis test using a particular test statistic, to construct confidence intervals using the quadratic formula. So it's kind of going back to high school or grade school to use the quadratic formula again. What's nice about this is that these confidence intervals have excellent coverage, even in small samples, like very small samples with very little compliance. The downside is that the confidence intervals can have an infinite length. I say that's a downside, but it could be the case that that actually is accurately reflecting our uncertainty when we have very little compliance. And these were used, this approach, broad approach, was used by both a paper by Kang et al. And Li and Ding both separately for the univariate IV setting. And so what we're going to do is we're going to apply this to this joint setting. And I'll just kind of describe how this method works to just give you a sense. I won't go through all the details, but the basic idea is that we're going to do an inversion of this test of null hypothesis that the ratio quantity of interest is equal to some value. And note that this is not a sharp null hypothesis. It's just a regular kind of null hypothesis, because this is an average, not an individual level. And so note that this is a ratio, so this is equivalent to the hypothesis that if we plug in the two ITT quantities of interest, right? And then if we do some division and move things to the other side, what we end up with is this hypothesis, which is that tau bar minus the null times delta bar is equal to 0. Right? And so once we have it in this form, actually what we can do is we can create the kind of obvious test statistic from this, which is just to fill in both of these missing these quantities of interest with their observed values, right? And this is going to be the test statistic for that, for this hypothesis test. And then what we can do is we can just take this and then figure out what is going to be the rejection region and invert the test. And because this has this nice form, what we can do is what ends up happening here is that this region ends up being a quadratic function of the null hypothesis. And once you have that, you can actually just analytically find what the confidence interval is going to be for any particular alpha to get any level confidence interval that you want. Again, the downside is that because it's got this quadratic formula form, these can have lots of different formats. They can be closed, so that they're kind of normal confidence interval. They can be disjoint, so it's like negative infinity to A, and then the union of that would B to positive infinity, or they can be infinite, or just the whole real line. So that's, again, whether you see that as an advantage or a downside, I think depends on what you're doing. And what we find is that both of these methods perform well, and I would say reasonably similarly when you have high compliance. What we see is that at low, kind of in simulations, we see that in kind of low compliance environments, kind of like other people have found, that this does very well, at least in terms of coverage. The actual kind of median length of the confidence interval is very big, but coverage is good.
Oh, quick question, Matt. So this so it reminds me of this randomization-based test, like inverting the confidence intervals that they do based on the null, the sharp null.
Mm-hmm.
Whereas like, I think that it's a paper by Inference and Rosenbaum
Oh yeah.
a while ago. And they also get this kind of infinite like intervals when the instruments are really weak. And I almost wonder that test statistics, could they use like a model-based test statistic under the sharp null?
Mm-hmm.
And so I do wonder there's some connection there. It maybe feels like they didn't do this inversion analytically, because they're sort of working in the finite-sample, non-asymptotic, just sort of, you know, just doing the Monte Carlo. But I do wonder there's must be some connection there. Feels like the test statistics is very similar, and the fact that you get this like infinite confidence intervals when you don't have much information, that also seems quite similar.
Yeah, that would be interesting to go back and take a look and see what the connection is, because we looked at the paper, I think, early on as just part of, seeing it in terms of the IV stuff, but not thinking so much about this part. So maybe that'd be good to go back and take a look.
But there's always some like connection between the sharp null and no sharp null. Yeah, as long as you're doing the randomization.
It's weird. Yeah, it's always, yeah. If you did a simulation-based approach too, I mean, maybe I just haven't seen it, but like simulation-based approaches that end up with these kind of disjoint confidence intervals, you'd have to have a very low compliance, I guess. So it's just, I haven't seen that as much. But yeah, it's a good idea. Any other questions before I talk really briefly about this application? Okay, so this is just the crosstabs of both assignment and an actual uptake for this experiment. So the people that actually receive cash and intended cognitive behavioral therapy. So the marginal compliance rate with the cash treatment is, like I said, is 98%, which is very good. I guess it's surprising that it's not higher, because it was actually a significant amount of money. The marginal compliance rate with the CBT treatment is considerably less. There's the original paper, they defined compliance to be a certain number of weeks that you actually went to the CBT. We've played around with, so that's somewhat problematic when it comes to, say, the exclusion restriction, because it could be the case that you were randomized, you went to like 2 weeks, and then you stopped, and we rate you as a not uptake, as like not taking the treatment, but you actually took 2 weeks of the treatment. So what we ended up doing is we've also done this various ways where we've defined it as, did you do any of the cognitive behavioral therapy or not? Is another way that we've done it to kind of minimize the exclusion restriction problems, and you get similar results. Yeah, okay, compliance here is the original paper. The one we're going to show you is 80%. And so because of this distinction between the two, basically perfect compliers here are the same as basically the compliers for the cognitive behavioral therapy, right? Because almost everyone complied with the cash treatment. Not everyone, but almost everyone. And so what our expectation should be is that the perfect complier effects and the marginal complier effects should be similar for the cognitive behavioral therapy, but they might diverge a lot for the cash. So, so what I'm going to show you is the effects on, again, a composite measure of the quality of social networks. So they measured like 30 items, lots of different things like, did you feel supported by your family? Do your friends engage in anti-social activities and things like that? And the two panels here are the short-term effects and the long-term effects. And so what we're going to look at here, and these are all in terms of standard deviations. So they're standardized. So these are just the ITT effects of cash. You can see that cash has an effect on short-term social networks, but not on long-term. And what we can see is that the marginal complier effects here are very similar. And then when we look at the cognitive behavioral therapy, the ITT versus the marginal complier effects are, very different in terms of their point estimates, but obviously the uncertainty goes up a lot when you account for that, the compliance rates. And then just one thing I'll fill in the rest of these, which are going to be these are the last square in each one of these is going to be the perfect complier effect. And you can see that there are some stark differences between at least the point estimates of for the cache treatment in terms of what it is for the marginal effect and what it is for the perfect complier. Not so much for cognitive behavioral therapy as I mentioned that you'd expect, but you can see some sharp differences. And note that there's only one of these for that interaction because the perfect compliers are equal to the marginal compliers there. So this isn't, overall the main kind of conclusions of the study are basically upheld by the replication that we did. We just across different measures, different outcomes, we do see some differences that can be somewhat sizable, at least before you consider uncertainty, between the kind of intent to treat or marginal complier effect and the perfect complier effect. So this is just to say that it can make a difference, like what compliance group you actually choose. So that's one thing. It also, I mean, you would see here that you might like have a more, your interpretation of the difference between these two might be different, again, if you were choosing perfect or marginal compliance. And so just to wrap up, I'll give a quick discussion, which is that, social science experiments often have both multiple factors and non-compliance on at least one of these factors. And so this paper is trying to provide a framework to handle both of these features in the same framework. So the contributions we're generalizing the IV assumptions and estimands to the factorial setting. We're going to differentiate between marginalized and perfect compliers. So just kind of recognizing the complexity of what that compliance brings in this setting. Define consistent estimators for the M cafes and the P cafes, and then provide confidence interval procedures that are valid in finite populations. We have a implementation of both superpopulation approaches and finite sample approaches that we talked about here in the R package, the Factorial IV R package. And so what's next, the things that we're thinking about in terms of moving forward are kind of continuing to think about different ways of weakening the treatment exclusion, including doing bounds analysis on those things, allowing for more than 2 levels per factor. So right now we're just 2 to the K, but what if you had N or M to the K, I guess? We run out of Roman letters in this paper, so we have to start over. Sensitivity analysis when compliance isn't or can't be measured. So this is in situation like mailers and get out the vote studies where we mail them, but we don't necessarily know whether or not people complied with them. So we have only partial information on compliance. And then handling the multiple comparisons in the setting, because obviously there are lots and lots of different effects that you're estimating, and we just kind of somewhat brazenly, assumed away this problem in this particular paper, but it is something that I think folks should think about. So that's all I have for today. Here's our site and where you can find the paper and the package for now, and I'm happy to answer any of your questions. I guess don't want to put Nicole on the spot, but I think we're happy to answer your questions.
Thank you, Matt. We are open to questions. So if you have questions, you can unmute yourself and ask questions. Okay, maybe I can ask one question.
Okay.
Yeah. So I wonder when the usual late effect and the M cafe diverge. Because if you think about the usual factorial experiment case, like your marginal effect is basically difference in means. I mean, the setting is slightly different, but you assume that it's the same as ignoring all the other factors, which is basically you marginalize over empirical distribution of that, compared to, like you estimate with the linear regression with all factors in there, and then you probably get finite sample wise, it could be different, but it's basically the same estimate. But in this case, I wonder, like M cafe, which is like a marginal late, basically, it's different from what people usually get. I assume people usually get late 1 factor at each, right? So I wonder when those effects could be completely different or diverge.
So,
does that question make sense? Yeah.
Yeah. I think in a narrow sense, and I'll let Nicole see if she has anything to say about it as well. But in a narrow sense, I think the thing that would diverge the most is from the kind of typical procedure would be the way we're defining the quantities of interest here in terms of marginalizing over the other factors evenly.
Mm-hmm.
And if you're in a situation where that, you, for some reason, that wasn't the case, or you somehow, you did that naively without kind of adjusting the quantity of interest, then those could diverge in some sense. But you could also redefine the MCAFE to be, to handle that situation as well. So I think you should be able to define them. We didn't do this in the paper, but I think you could probably kind of come up with a relationship between the two.
I see. So particular way of choosing weights, how do you marginalize over other distribution might be give you that weight on
so
one particular factor.
It's just complicated because you have to, so we haven't defined in this paper, like the composite, like how to collapse the potential outcome, but you have to come up with some way to collapse the potential outcome across the other factor in order to get the y of 1 that you would y of 0 in the univariate case. And so to say that they're the same, we'd have to come up with some way of doing that. So I don't know, Nicole, do you have any?
I think the only other thing to add is just, I think it's important to take into account the factorial structure, especially in terms of assumptions here, right? Because basically, if we aren't thinking about that, then the uptake on your other factors can change based on what you were assigned to. Like if we're interested in the marginal effect of factor 1, your uptake on factor 2 could change based on whether you're assigned to level +1 or -1 of factor 1, unless we have that assumption that we're making in our paper of treatment exclusion. And so if we just kind of naively ignore the other factors, we're maybe not looking at basically the really pure causal effect that we think we are, because there are other things on the other factors that are changing as well. Does that make some sense?
Right, I see. But I thought at the same time, if you naively compute one factor late, you're not assuming any like compliance structure for other factors. For example, you don't have to assume there's no defiers in factor 2 if you're looking at factor 1. Maybe I'm wrong.
Yeah, so I guess what I'm saying is your interpretation would be different, right? If
yeah.
About the factorial and you're not making those assumptions, then sort of how you are interpreting what that means is going to be different.
Thank you.
Yeah, you could always, I think you could always do weaker assumptions to get, if you're only interested in one of the two factors, you could obviously, I think you could always make weaker assumptions.
Yep, there must be some equivalence results between these estimators, the ratio estimators and the two-stage squares with some instructions. Is that right?
Yeah, I mean, so yeah, in the paper that the 2x2 paper that I wrote, that paper has like at least, it's a different set of quantities of interest slightly, like they're defined in a slightly different way. But we do, I was able to get like a relationship between two-stage squares with interactions and these quantities. They're not, some, the marginal terms in there are kind of weird, but the interaction does identify the interaction among perfect compliers in the 2x2 case.
But does that generalize to this case, or?
No, I don't think so. Not straightforwardly, because because that proof assumed independent assignment across the two. So it may be the case that that you could weaken that assumption and it would still hold. But at least what I proved in that paper, it wouldn't apply to this case straightforwardly.
But it feels like if you have an interaction, it will go through.
Yeah, I think so. I'm not like, I mean, we haven't shown that, I guess. Is what I'm
saying.
Any other questions?
I have sort of the obvious one.
Yeah.
Which is there's uncertainty in the results due to the assumptions, and there's uncertainty due to due to whatever application you're using, how often do you, what's your intuition? I mean, clearly the problems you're identifying are definitely there in real analyses. But if we apply this method, or we don't apply the method, but we recognize the uncertainties, how often will those uncertainties be bigger than or smaller than the confidence intervals in the analysis, so that we actually wind up with a different result?
You mean you're talking about compared to what the kind of a reasonable analyst would do with the same data, like without knowing this?
Well, I mean, yeah. So clearly, like a reasonable analyst would make mistakes because they would assume all the things. They would make assumptions that shouldn't be made.
Yeah.
So that's the first thing. So first of all, if they do nothing else, they should, just to be appropriate, increase their uncertainty intervals. Okay. So they're going to ignore that. Okay, that's the first thing. Then you're going to come along and you're going to say, we're going to recognize that the uncertainty intervals are larger, but then we're also going to estimate the quantity of interest in a better way. And that's going to produce a different set of estimates with a different set of confidence intervals. And what I want to know is, sometimes you say, look, sometimes we all say, look, here's a better method under certain assumptions, which produces, of course, larger uncertainty intervals. But the uncertainty intervals are larger than the change in the substantive result that would result. So, you know what I mean? Like, yeah. How often does this matter in practice? So it's hard to know exactly.
No, I mean, but I think this is, just my intuition from looking at IV stuff a decent amount is that the uncertainty that ends up happening by like accounting for the compliance rates, especially with low compliance rates, is massive compared to like the differences between the point estimates. So often, at least in the kind of field experiments that I've seen where compliance is really low, like it's going to be the case. And there's always going to be this trade-off where the bigger the problem of non-compliance, the more opportunity there is for a change in the effect, like the point, so the point estimates to be different, but usually that also accompanies like big changes, big increases in the uncertainty that go along with that. What the gradient on those two things, it's like a race, I think it's like a race that you're kind of indicating. It's like, well, do they basically just, stay the same so that we never, the confidence interval just keep getting bigger, but the point estimates might change, but it's always the same basic thing. Overall applications, I don't know. I think, but I do think, one thing to consider though is that we're not just like changing the method, but we're actually like answering different questions, like a different quantity of interest. And so yeah, you could come up with bad ways of doing it for that particular quantity of interest, but what we're focusing on is this different quantity of interest. So the difference between the effects that I showed you there are just like, what question do you want to answer? And you're giving different answers to those questions. And those different questions, by their nature, lead themselves to different levels of uncertainty. So we don't, so there's no, as far as I can remember, there's no other method that's been proposed for these quantities of interest in particular. So that's a difference, I think. So other than, I guess, making the assumption that there is no non-compliance or non-compliance is not a problem or whatever. You could, I guess that's technically a method. But yeah, I don't know. Across the space of all problems is always a hard question to ask.
No, but it's not really across the space of all problems. It's more like, yeah, when I look at the 20 examples of where you could go through the effort, it would be some effort to figure out how to do it the right way, implement this method. Across those, obviously you don't know until you run the analysis, but my best guess, because your best guess, because you would know, you and Nicole would know better than we would. You gave me a part of the answer, which is everybody has way bigger uncertainty than they're admitting to. Okay, I totally believe that. Okay, but if all we say is everybody's more uncertain than they are admitting to, then we're being scientifically correct, but we don't get anywhere that way. No one's gonna pay attention to us. We got to go one more step to get them to use the methods. which is not only that they're more uncertain and they should really report their t-statistics by dividing by 12, but instead, actually, if they pay attention and they change the quantity of interest and they carefully choose the right assumptions and they use these different estimation methods, that they will get a different, qualitatively, substantively different assumption. Okay, and that will happen of the 20 examples that you've looked at 7 times. You know what I mean?
Yeah.
What's your wild guess?
Yeah, I would say like in all the estimated effects that we've come up with, I would say it's like, this is just purely my interpretation of them would be like, like a 15 to 25% are the effects between 2 different quantities of interest are different, or kind of quote unquote substantively different in some way.
Yeah, I mean they're totally different things. In some sense, they're not comparable, but
no,
in another sense,
you would
really
come to different conclusions about the problem. That you would like make different, like you would, as a substantive researcher, you would write your paper in a different way. I feel like if you'd use this this estimand versus this one, even though they're answering what on their face seem like similar questions.
And your big claim at the end of the day is that's going to happen a lot-ish, right?
Enough
pretty often, or
yeah,
it's not going to happen once out of 100 times because you wouldn't have written the paper, right? It's got to happen, out of 20 times, it's got to happen 5 times,
Sure.
4 times.
Yeah.
I don't know.
Yeah.
Right, but that's what and we don't have any. I'm not asking for evidence, but your feeling is that it would be at least that. Is that right?
Yeah.
I mean, there's a lot of problems.
Yes,
there's a lot of problems in saying that, because if you asked all the original researchers to go use this method, they would all defend themselves. I just mean, what is the actual correct answer? If you two went after each of these applications and did it in the right way, and you didn't try to just make a different answer, but like substantively, you took the author's questions, not their specific quantity of interest, because you have a better one, or an answerable one, but their specific substantive question. You provided an answer. How often would a substantive researcher who read your results say, "Yeah, actually, I'm going to write the textbook in a different way"?
Yeah,
that's sort of what we really want to know at the end of the day, right?
It's a very political methodology bar to me.
Yeah, it's a bar we put. That's exactly right. That's our bar. I mean, it's social science methodology bar. I'm just looking at my friend Chris here. That's the bar we put, and the statisticians don't have that bar, and the computer scientists don't have that bar, and nobody else. We have that bar.
I think just to briefly, I think it's similar. I think it's if we benchmarked it against other methods, other new methods that are coming out, I think it might have a similar performance. Like a bake-off, if we were to just like take, this is like a meta thing, but if we took let's take 5 new methods that people have come up with in the last year, and we did
to do unrelated things.
Yeah, like whatever, just go apply them in all the possible problems. I think we would come out in the pack, like right in there.
Okay, good.
That's my best. That's as far as I'm willing to give guarantees. I'm willing to give you.
You did exactly the same thing as you did in the paper, which is change the quantity of interest and answer that question, which exactly. I like.
Can I add in there though?
Yeah.
So I think when you get the same result, there are 2 things that could be going on. One is sort of the structure of the problem is not sufficiently different that methodology makes a difference. The other is luck, right? There's always this famous, saying that, a broken clock is right twice a day. And, it makes I think a very big difference whether we're talking about, getting different results or not getting different results because somebody was lucky, or the structure of the underlying problem is such that your method really doesn't make much of a difference. So it's just a thought, and I worry a lot about sort of how lucky various people are out there, which is, they use methods that should not give the right result, but it's just like the clock.
Yeah.
So I was thinking one direction that you could, I mean, you've done this, I think, to some extent in the paper already, but sort of characterizing these different types of compliers. So I think when you have like principal certification with lots of treatment, the problem is like the number of types just explodes, which makes it kind of difficult to like characterize. So one potential approach is like marginal, I just average over. But that doesn't sort of give additional information. And so it feels like maybe like either clustering, so you can say, okay, there's like, 20 possible types, but actually there's 3 broader types that have these type of effects. Or like either, I'm just trying to think about either like cluster based on like different characteristics, the covariates you have, or the effect sizes that like there's a group of people who have big effects, small effects. So like trying to come up with some quantities that like standard methods can't really produce. So in addition to sort of refining the standard quantity of interest, that are sort of interpretation-wise somewhat different, but still kind of similar, like the effect of A. But try to give them more like information, So I don't know if you sort of thought about that or.
Yeah, this is not quite the same as what you're talking about. This is maybe partially related, which we've thought about doing but have not done, is that you could extend fairly straightforwardly. It would be like the Abadi way of profiling different compliance groups in terms of the covariates, so that you would use similar kind of a weighting structure to what he did in order to kind of say how do the compliers look versus other groups in terms of the covariates, and you could do something similar here for the different compliance groups that we have. And then from that, you probably could do some clustering, like you said. That might be one in to the kind of clustering that you talk about, to at least come up with what are similar types. Are these similar in some way in terms of the covariates? But no, in terms of like clustering, the actual effects themselves, the like heterogeneous treatment effects across the different types. No, we have not thought about that, or I haven't thought about that. That's a good one way to go. Although we're like power in this setting is so hard that interactions are bad in and of themselves, but then having non-compliance, you start to run out of power very quickly, which is why I suspect the limitation of this method the most is that I think it's like just of all the factorial things, it's like you run out of power. I don't know, Nicole, did you have?
No, I think that's a really interesting idea. So the idea, Kosuke, would basically be cluster people so that you kind of have these clusters of people who react similarly, and then now these marginal effects, because we're still not gonna be able to, I don't think, identify, this cluster necessarily is this type of compliers, but at least the marginal effects are more meaningful, is your thought.
So it's basically modeling the compliance probability given the covariates, and then characterizing, I guess not the individual per se, but I guess a group of people who have similar like compliance type, like patterns, I guess.
Right. So then at least your marginal, because it is true, your marginal is just you're averaging over all sorts of.
It's sort of like okay.
Yeah, that's a good point.
That's related to the Peter Erno's work on this, where if you would do the additional step then of making an independence assumption conditional, that conditional on those covariates, you've measured enough covariates to make compliance orthogonal, then you could start to do things like get different interesting quantities of interest. So that's an interesting, that'd be another inroad.
All right, I guess that's all the good discussions that we have. Thank you for initiating that. Thank you so much, and we're gonna meet on Zoom next week. So
Thanks
see you
everyone
everyone.
for coming in. Thanks for bearing through the technical difficulties.
Thank you, everyone.
Thanks, Matt.
All right.
Take care.
Bye, guys.